Hello everyone, and welcome to the PCD for Weekly Contest 457, right? Um, I'm Vibhaas from TLE Eliminators, and let's get right into the problems. Before getting into the problems, I'd like to say that TLE Eliminators self-paced courses are live right now, right? So you can go to the website tleliminators.com and you can go check them out. The courses are in 4 different levels, which include more than 40 hours of recorded lectures, more than 100 curated practice problems, hints and video solutions for each problem, as well as doubt support, which is available almost 24/7, right? You can make a doubt anytime you want, and a mentor usually picks it within 10-15 minutes, and you can discuss your doubt with them, right? So, for an ordered way to approach competitive programming, do check out TLMinator self-paced courses. Okay, so how was the contest, guys? Am I audible? Can someone put in the chat? Uh, am I audible? How was the contest? Last one. Yeah, last one was a bit hard, I can say. But I would say that A, B, C are a bit standard. So A was a very easy question, and then B was basic graphs, C was basic DSU. D was a bit ad hoc. Okay, guys, let's get into the question. All right, let's get to the questions. Problem A. So I don't think we need too much time on problem A, but I will still read the question and discuss it with you, right? You're given 3 arrays of length n that describe properties of n coupons, right? Um, The first array is code, the second array is business line, and the third is active. Okay. The ith coupon has code of I, which is a string representing a coupon identifier. Okay, so it's like the ID of the coupon. Business line is the business category of coupon. Is active is a boolean which says whether it's currently active or not. Okay. A coupon is valid if all the conditions hold. Code of I is non-empty and consists only of alphanumeric characters. Okay, and underscore. So alphanumeric means A to Z and 0 to 9, right? And underscore. So the ID should only contain these things. Like the code should only contain these things. Business line should either be electronics, grocery, pharmacy, or restaurant. Okay, and is active should be true. Okay, so these are the conditions for a valid coupon. Now, when we need to, what do we need to return? We need to return the codes of all valid coupons sorted by their business line. Okay, in this order. Electronics should be first, then groceries, then pharmacy, then restaurant. Okay, so we need to sort by the business line and then by code in ascending order. Okay, so I guess the question is understandable, right? So how do we do this? The way I did it was very simple. Um, so let n equals, let's say, code dot size, right? So this is problem A, and that will be the number of elements, right? Then I made 4 vectors. Okay, I made 4 vectors, made 4 vectors. You can do it in many ways, right? You can make one vector itself and sort using a custom sort function or something. But I made 4 vectors, okay, A, B, C, D, and then I just checked the condition. Okay, so the first condition is that it should be alphanumeric and it should be or have underscores, right? So I checked if like for I from 0 to n, right? I checked if it is alphanumeric. So if is alpha for each character C, right, in the code, um, like in C++, we can write is alpha is num, right? Um, like that, right? So I checked if it's a valid code, right? If it is not valid, I can just continue, right? If not valid, I can just continue. Um, like we have to do this for each character, okay? For X in code I, okay? We need to check for each character if it's valid or not. And then we can check if the business line is one of the 4 categories, right? Um, Electronics, pharmacy, or restaurant. So directly we just need to compare strings, right? If business line equal to, like if it's not any of the four, if it's not electronics or if it's not pharmacy and so on, right? Um, and business line not equal to pharmacy, right? And so on and so forth. We can check all four. So if none of them are true, we can say that it's not valid. And if it's not active also, we can say that it's not valid. So I can just directly show the code because it's a very implementation based problem. Um, is it means whether it's valid or not. So that's the variable I put. So if the code was empty, right? If the code has 0 characters, then also is it will be false, right? Because the code must be non-empty. Then if any character is not an alphanumeric and is not underscore, I set is it to false. Similarly, um, if the business line is not electronics, grocery, pharmacy, or restaurant, I set is it to false. And if it's not active, again, I set is it to false, right? So this will check whether it's valid or not. Then after that, based on what the business line is, I push it in a different vector, okay? So if the business line is electronics, I push it in vector A. If it's grocery, I push it in vector B. If it's pharmacy, I push it in vector C. And if it's restaurant, I push it in vector D, okay? So based on business line, I pushed it in a different vector, right? Based on business line, I made 4 vectors in the start, right? So based on vector business line, push it in A, B, C, or D, okay? And then we know that we need to sort these vectors, right? And then also there should be like electronics should be first, then grocery, then pharmacy, then restaurant. So I know that A only contains electronics, B only grocery, C only pharmacy, and D only restaurant, right? So I sort each of these vectors and then I push everything from the other vectors into A. Okay. So I sort A, B, C, D. Then all elements in B I push to A, all elements in C I push to A, and all elements in D I push to A. So basically I'm appending the vectors B, C, and D to the vector A. Then I return the vector A, right? And this is our answer. What is the time complexity? Um, if we let n equals the length, right? So the time complexity will be at most n log n because we are doing sorting. And since we are sorting on strings, it will compare two strings, right? So it will be n log n times length of the string, right? So code I dot length, right? So right, and the maximum length is 100. So we can say that this will be um, n times L times log n. Okay, so here n goes up to 100 because the 100 n is literally given as 100, and the max length of code I can go up to 100. So this is the maximum time complexity for the problem, right? Worst case time complexity for this implementation. All right. So that's how you implement this problem in C++. If there are any doubts, ask it now. Otherwise, we'll move to problem B. Okay. I think the first problem is just implementation, so there's nothing much to discuss about it. I'm not sure who's doing biweekly PCD, so I'm not sure when it'll come or whether it'll be done. Okay. Second problem, power grid maintenance. We are given an integer C representing C different power stations which have some unique ID. They are connected via some cables where each connection is given as UIVI. And then initially all stations are online. We are also given a 2D array queries where each query is of two types, one X. In this, we do a maintenance check for station X. If station X is online, then it resolves the check by itself. If station X is offline, then it is resolved by the power grid, the smallest ID in the power grid of X. Okay. If no operational station exists in that grid, return -1. Yeah, we can directly sort by taking as a pair. That also works, CV coding. But the thing is, we need electronics first, then grocery, and then The order is not exactly alphabetical, right? So you need to keep that in mind. Okay. So we are doing problem 2 now. Yeah. So then 1x means a maintenance check is requested for station X. They have defined how maintenance check works. If no operational station exists in the grid, return -1. Now 2x means that the station X goes offline. We have to return an array of integers giving the answer for every query of type 1. Okay, so that's the question, right? So how do we approach the problem? So now the first thing to note is the stations form a graph, right? The stations form a graph, right? This is the first thing to note. And the cables are the edges. Cables are the edges. Okay. Now, we are doing some queries on the graph, right? In some queries, a station goes offline. In the other queries, we need to know whether that station is online or we need the smallest ID in the same power grid. So here, let us take the second example and try to understand what's going on. So in this C equals 3, that means that there are 3 stations. So our graph has 3 nodes. Okay. So let's say our graph has 3 nodes. Example number 2, right? From the problem, we're doing example number 2. Our graph has 3 nodes, 1, 2, and 3. Okay. And what this means is there are no connections in the graph. Okay, so it's given that there are no connections in the graph at all. That means this is a separate power grid. This is a separate power grid. This is a separate power grid, right? Power grid was defined to be a set of stations which are reachable directly or indirectly. Okay, so now we have that all these 3 are different power grids. Okay, so as soon as one goes offline, we can't use it again, basically, right? So at first we ask, is station 1 like we query station 1, right? So station 1 is on, so the answer is simply 1. Now we have type 2 query for station 1, and that means that station 1 went offline. So we can say that station 1 went offline. Now when we query for station 1, it's offline and everything in its power grid is offline, right? There's only one thing in its power grid and that thing is offline. So that's why the answer is -1 for the second time we query station 1. Okay. So the answer is +1 for this. There's no answer over here, right? Nothing changes in query 2. And then the third one, the answer is -1 because now station 1 is offline. Okay. Now I'll do my own example. Um, example, right? And let's say we have a graph, right, which is our stations and the cables. Okay. So this is my graph, and I'll give some numbers to the nodes, right? So we have some numbering, 8. All right. So basically, what the question is saying is, if I query the station 2, okay, I'm querying the station 2 with a type 1 query, okay, type 1 query for station 2. So if the station 2 is on, I can simply give the answer of station 2, right? But let's say the station 2 was off, like some other earlier query had turned it off, then I need to give the minimum value in the power grid, which is on, okay? So let's say if station 3 is off and station 1 is also off, then we should answer 3, right? And the reason is, what is the power grid over here? From the definition, a power grid is all the stations which are reachable directly or indirectly, right? So we can understand that power grid, what they mean by power grid in the question is simply connected component, right? It means connected component of a given node, okay? of a given node. So if you're not familiar with graph theory, do check it out. Usually LeetCode's second problem is not graph theory, but this time they were more theoretical. So the second problem itself was graph theory. If you want to know in TLE Eliminators, graph theory is covered like somewhere in level 3, a little bit in level 3, and a little bit in level 4 as well. But like the basic graph theory like BFS, DFS, you should know, right? Like how to find connected components is a very basic graph theory thing. So yeah, if you're doing lead code where they ask theoretical questions more, then knowing some amount of graph theory is always helpful, right? So the power grid is just a connected component of the given node. So what is query of type 1? Query of type 1 says, let me use some other color. It's getting a bit confusing. Okay. Type 1 query. Let us rewrite it with our understanding that power grid just means connected component. So type 1 query means if node X is on, then we can say that answer is X to this query. Answer to query is X. Now, if otherwise, in all nodes of connected component which are on, so of connected component of X which are on, um, answer to query is the minimum ID. Answer to query is minimum ID. Now, if no node in this connected component is on, if all nodes in connected component of X, okay, component of X um, are off, then answer to the query is -1. Answer is -1. Okay. So this is what we understand of type 1 query. Okay. This is the current understanding we have of type 1 query. Now, so we understand that step 1 should be um, steps. So the step 1 will be find all connected components. Okay. Find all connected components, right? And label the nodes and label the nodes with connected component ID. Okay. Connected component ID. Okay. And how do we do this? This is a uh, standard or theory idea using DFS. Okay. Using DFS. So this is our first step. What does this look like in our example graph? Well, if we start in this graph and we start at some node, if the node has not given an ID yet, let's say in the start, the connected component ID is -1 for everything. Okay. So the color or connected component ID. So sometimes it's called color also, right? So each connected component can have a different color. So that's how I like to think about it. The colors are 0, 1, 2, so on. Right. So in the start, the ID is -1, and the next color or ID we can use is 0. Right. ID equals 0 is there. So when we start at the first node, this node and all the other nodes reachable by a DFS, right? All the nodes reachable by a DFS will be in the same connected component. So what we can do is we can change the connected component ID to 0 over here. Now we go in our DFS, we reach here. So this also becomes a 0. Now in our DFS, let's say we reached here, or we reached here. So this one also becomes a 0, right? And then this one also becomes a 0. Now in our DFS, we reach 3. So this one also becomes 0. So we can say that the ID of connected component of each node is 0 for this connected component. Okay. Now as we go in our DFS, we don't do a DFS here since ID is already set. We don't do a DFS here since ID is already set. We don't do a DFS here since ID is already set. We don't do a DFS here since the ID is already set. Now here the ID is not set. So we set it to the next ID, which is 1. right? The next ID available is 1. So we set this 1. Now we do DFS and set the IDs in the same component. So we set this to 1, set this to 1. And this is how we find all connected components of a graph. Okay? This is how we find the connected components of a graph using DFS, and we give each connected component a different ID. Okay? So this is the first step using DFS. I'll show you the code for this. Although I think if you have studied basic DFS also, you would know how to do this, right? It's a very standard thing. Now what we can do is make a vector of sets. Okay? So whatever the equivalent is this for Python and Java users, but we'll make a vector of sets for each connected component. For each connected component, there will be a set. Okay? There will be a set, and that set will have all the active active nodes or stations of the connected component. Okay, I hope that's understandable. That for each connected component, we'll have a set, and that set will have all the active nodes for the connected component. Okay, and after this, the question is mostly done because a set is already ordered, right? So if the value x is there in the set, we can give the answer as x. Otherwise, we can give the smallest value in the set. If the set is empty, the answer will be -1. And for type 2 queries, for type 2 queries, um, for queries, for type 2 queries, we just need to remove that element from the set, right? So type 1, so let ID equals connected component ID of x, right? So 1x, so this is the type of query, connected component ID of x. Let our vector of sets be v, okay? Let's call that v. So then v of ID, if it has the value, so we can use set.count in C++. Depending on your language, it will be something. We just need to check if x is there in the set or not, right? If this is true, if this is 1, then answer for this query is x. Otherwise, if the set is empty, right? So if this is size equal to 0, then answer will be -1, right? Otherwise, answer will be the smallest element. Okay, so answer will be the smallest element in the set, right? So this set is all the nodes in the connected component. And for a type 2 query, we simply remove that node. So we can just say that, let's say, yeah, dot erase x. So basically the set of that connected component, whichever x is in, we're going to erase x from that set. Okay, and this is the whole code for the problem. Like this is the whole pseudocode for the problem. And to be honest, it was a direct question, so there's not much intuition. If you know connected components topic, you will be able to solve this. Time complexity. So number of nodes was C, right? Number of nodes was C, and number of edges. So the number of edges is N, right? That's the number of edges, correct? Yeah. So time complexity of DFS is edges plus nodes. I hope you know that. So that is CA plus N plus for each query plus to create this vector of sets, because set has a time complexity of log, so it will be C log C plus for each query we are doing a log C operation, right? So plus Q log C. So this is the time complexity of the code. Okay. Why? Because here DFS is big O of C plus N. Then to create sets, it's C log C, right? This is big O of C log C. and this part is big O of Q log C. Okay, let's have a quick look at the code. So in the start, we are first converting to adjacency list, right? Because we want to do DFS, so we want adjacency list. This color basically means the ID of each connected component. Okay, so this is the ID of connected component. I like to call it color for some reason, but you can just imagine that this stores the ID of for each node which connected component ID it is in. Okay, so then first for each connection we push back into our adjacency list. Okay, then we set the color for everything equals -1. Right, in the start all the IDs are -1, and then if the color is -1 for some node, we do DFS over there, and in that DFS we set the color to the current color. Okay, we set the color to the current color. We visit all adjacent nodes and do DFS over there as well. Okay, if the color is not set, we visit it and we do DFS over there as well. So this is the simple DFS code for that, right? Simple DFS code for that. Then once we have already assigned all the IDs for all the connected components, we can create our vector of sets, right? For each connected component, it has a set of the active nodes. So for each connected component, it has a set of active nodes that can be simply made by v of color of I dot insert I. So for its color component, we're inserting the ith element. Okay. Now we are ready to answer the queries. For each query, X is the node ID. Okay. So that's Q1 minus 1. If the query is type 1 and type 2, we have two cases. Okay. If it's type 1, then if the value X is there in its connected component, then we can simply push back X, right? Otherwise, if the connected component size has become 0, we can push back -1. Otherwise, we push back the first element of the set. Okay, we push back the first element of the set. Note that +1 is because we are storing in 0 index. That's why +1. Okay. Otherwise, for type 2 query, we simply need to find that connected component and erase the value X. Like if the value X was if the value X was there, then we erase the value X. Otherwise, we don't need to do anything. Okay. So this is the whole code for the problem. We're doing a DFS, finding connected components. For each connected component, we create a set. Then if the value is there in the set, we can push X plus 1. If the set is empty, we push -1. Otherwise, we push the smallest element of set. Here we simply erase the element in the correct set. Okay. So that's the full code for this problem. Right? Is the problem B understandable? Any doubts, please put it in the chat, guys. Is the problem B understandable? Okay, so let's move on to C. All right. Okay, so before we start C, I would just like to say that you need some familiarity with the disjoint set union data structure. Okay, so like even if you did not know what connected components are before B, I think you could have understood by the explanation. But to understand disjoint set union, you will need to read some theory. Okay, it's not something you will understand just from the video. So we can say problem C, and it has a prerequisite of disjoint set union. Okay. If you want to understand disjoint set union, obviously there are videos on YouTube, as well as I think it is there in TLE level 4. Okay. And I think Codeforce's EDU also has disjoint set union. B was harder than C. I don't really think so. Like for me, B was definitely much easier because connected components seem to be as more easy concept than DSU. But okay, it depends on the like person also, right? If your DSU is strong, I think you will get problem C pretty simply. Okay, so let us go through the question now. You are given an integer n, undirected graph of n nodes. Okay, so it's again a graph problem itself. Then there is a 2D array edges. Okay, there's a 2D array edges, u, v, and time. Okay, and then there's an undirected edge from u to v, which can be removed at time of t, time of I. Okay, you're also given an integer k. Initially, the graph may be connected or disconnected. Your task is to find the minimum time such that after removing all edges with time less than equal to t, the graph contains at least k connected components. Then you return the minimum time t. Okay. So basically, over time, more and more edges get removed, and we need to find when k connected components are there. Okay. So that's what we need to do. Let's take an example somewhere. Yeah. So their examples are small n, but I think that is fine. Like the question is not too hard to understand. Example. Um, so this is the given graph. We have one, uh, okay, 0, 1, 2. Nice, it's zero indexed itself, and 2, 4. Right. And what do we want? We want three different connected components. K equals 3 means we want three different connected components. So what happens at time equals 2, at time equals 2, these two get disconnected. Okay, at time equals 2, these two get disconnected, right? And now we have two connected components, right? In the start, we had only one connected component since everything was connected. Now we have two connected components. Okay, now we have two connected components, but it's still not three connected components. We want three, right? So what next? Um, Now at time equals 4, this edge gets removed. Okay, at time equals 4, this edge gets removed. And now we have three connected components, right? So the minimum time is 4. Okay, minimum time such that we have three connected components is 4. Okay, now for the same question, if we had k equals 2, right? If k was 2, then the question would be at what time do we have two connected components, correct? So for this, we can see that simply remove this edge, right? At time equals 2, we remove this edge. Then what happens is, then what happens is, um, if this edge is gone, now we have two connected components, right? So our answer will be 2. Since this is the minimum time, we have two connected components. Okay, so that's basically how the problem works. We need to find the minimum time for there to be at least two connected components. Okay, now, so if you knew the disjoint set data structure, this idea would be pretty simple to understand. And the idea is we will do it in reverse order. Okay, so I'll jump right into the idea since it's a very theoretical question. There's not much thinking. There's just the idea itself. And the idea is instead of removing elements, instead of removing edges in ascending order of time, in ascending order of time, what we will do is we will add edges in descending order of time. Okay, descending order of time. And why are we doing this? Why are we doing this? Because when we are adding edges, when we add edges, then we can maintain a DSU, right? We can maintain DSU data structure. We can maintain DSU data structure, which can tell us, DSU can tell a lot of things. It can tell whether two nodes are in the same component or not, and things like that. But we just care right now for the count of the how many components are there, right? So then when we have a DSU, it will tell us how many components are there at a given stage. How many components are at any given step, right? we can get the answer using the DSU data structure. Okay, so I hope this much is clear. When we add an edge, we can maintain a DSU data structure and we can find out how many components are there right now. Okay, so that's how DSU works, right? Like DSU maintains the components internally. Okay, so this is the core idea for the problem. Okay, like we have to do it in reverse order and add the edges. I'll give you an example for what I meant. Okay, example, and I'll solve it. Let's say my own example, right? So let's say we had a graph like this. Okay, and the time to remove the edges are 2, 4, 3, 5, 7. Okay, or let's say this is 5 and this is 4. Okay, now this is our example graph, right? So originally we remove small edges, like we remove this first, right? And then we can say that, okay, whether we have reached our k disconnected components or not, right? So let's say we want k equals 2. Okay, let's say we want k equals 2. So we first remove this one. It's still not disconnected. Then we remove this one. Now we have two disconnected components, right? So this is how we do it forwards. Okay, but to do it backwards, um, so if we do it backwards, we are going to imagine that there are n connected components at the start, right? At the start, there are n connected components, and all the nodes will be disconnected. Okay, so in the start, all the nodes will be disconnected, right? Now, when we add an edge, we'll add the highest weight edge. Okay, so first we'll add the highest weight edge, and in the start, the number of connected components, we'll call it CC, was 4. Now, when we add this edge, the number of connected components becomes 3, correct? Okay, now the next edge we add will be this, right? And now the number of connected components becomes 2. Okay, and now this is what we want. We want two connected components, but what happens is that's not the minimum, right? So we can keep adding edges, right? We can keep adding edges. Now we add an edge over here, right? Okay, wait, sorry. Since this edge is 5 and this edge is 4, this will be added first. Sorry about that. So 7 will be added first, then the 5 edge, then the 4 edge. Okay. After that, we add the edge 3. Okay. And now the number of connected components drops to 1. Right. Now the number of connected components drops to 1. And as soon as when we are doing this in reverse order, when we do in reverse order, the number of connected components becomes less than k, right? At whichever step it becomes less than k, that means that if we do not do this edge, right, it would be k, connected components would be exactly k, right? So at that time, we can say that at this time, we can say that we have found our minimum time. We have found our minimum time, found our minimum time, okay, which is our answer. So let me just summarize what I said. If you do not understand the logic, then I'll show you an example as well. So summary, um, sort by highest weight edge, right, or highest time edge, then create a DSU, create a DSU where all nodes are disconnected, right? All nodes are separate connected component, separate connected component. Repeatedly add edges, repeatedly add edges in the order which they are, right? Sorted highest time to lowest time. The first point, such that using the DSU DSU, the number of connected components in the DSU becomes less than k, right? The first point where it becomes less than k, the time at this point is the answer. Okay, the time at this point is the answer. Okay, and that's because if this specific edge, which just made the number of connected components less than k, if we had not added it, right, then the connected components would be exactly equal to k, correct? So that's what we want, and that's the answer. Right, so we're doing the whole process in reverse using a disjoint set union data structure. And if you have studied DSU, this is a very standard DSU question. I think anyone who has solved more than 5 questions of DSU should be able to solve this question, in my opinion. Like if you realize that it's DSU. Okay, and if DSU dot connected components was never less than k, right? Was is still greater than or equal to k, is still greater than or equal to k, even after adding all the edges, then the answer will be 0. Okay, so that's the special case. The answer will be 0. If the if in the start itself the number of connected components was greater than or equal to k, then the answer will be 0. Right? At time equals 0 itself, we have got the answer. Binary search is also used. I guess we can use binary search, but then the time complexity for DSU should be better, right? Yeah, I think binary search also makes sense. Makes sense. Makes sense. Right. So if you do not know DSU, then binary search will also work, right? You can binary search which time is the correct time, because all the times greater than the time will have greater than equal to k components, while less will have less than k components. So then in that case, it's a simple level 3 problem, right? Binary search and graphs. DSU is a level 4. So yeah, it's a roughly level 3 or level 4 problem. So here is just the template which I have for DSU, right? If you just Google DSU template, you can get your own template, I suppose. Or otherwise, you make your own template, learn DSU and make your own template if you don't have one already, right? So this is just a DSU template, which I just copy pasted here. Okay. Yeah. So here, for some reason, the number of edges can be 0. So in that case, you just return 0. All right. So this was a special case. I got a wrong answer. I saw the number of edges could be 0. So I'm just handling this case on top. Now I will sort the edges by descending order of time. Okay. So here I'm sorting the edges by descending order of time. Now, my initial answer is the maximum edge weight, right? Because once you have disconnected all the nodes, then definitely, like, once you have disconnected all the nodes at the final time, right? Then definitely, like, that is the maximum possible answer, right? Now here I'm defining a DSU, right? Here's my DSU, which I've called U, and I'm saying that it has n nodes. In the start, they will all be disconnected. Now DSU.unite is my function for uniting in my DSU. So I will unite the given edge. Okay. Now if my count of my nodes in my DSU, right? So the way I have implemented it, count is the number of connected components. So if my count of my nodes in the DSU has become less than k, that means just now, they have become less than k connected components. That means my answer is simply the time of this edge. Okay, the answer is simply the time of this edge. So I can set that to my answer and break. If in the very end, still the number of connected components is greater than or equal to k, then my answer is 0, and I can return my answer. Okay, so that's all. This much is the code. If you have a DSU template, the code is very small for this question, right? Yeah, C was, no, I think both A, B, and C were intuitive for me, so I have no idea. Binary search and DSU. I don't see the point of doing both. I don't see the point of doing both. Okay, so the time complexity for this should be how much? Um, so for sorting, the number of edges, right? So let's say there are m edges. So we're sorting all the edges, so it'll be m log m, right? And m log m plus how much? So for each edge, right, we're doing m times. We're adding to our DSU and deciding based on that. So all the operations of DSU will be big O of 1 or at worst big O of inverse Ackermann, right? But here to the DSU is very basic, right? Only the unite operation is itself being used. So we can write it as M, and this is the inverse Ackermann function of M, right? So if you don't know what inverse Ackermann function is, Google it. The unite operation of DSU and all they use roughly this time complexity, which is big O of 1 almost, right? Inverse Ackermann function is like 2, 3, 4 for even large values. So in practice, it will be big O of 1 itself. So in practice, the time complexity is just m log m plus m. So the overall time complexity will simply be m log m for the DSU solution. Okay. So this is the time complexity of C. Any issues, or we'll go to the next question? I applied binary search to be safe. Yeah, binary search would be overkill for this, I suppose. But yeah, binary search is also perfectly fine. Like both the approaches are perfectly fine. Only thing is binary search approach will be, I suppose, slightly higher time complexity, not even much, right? Because this one also by sorting it has this log factor. So there'll be not much difference. Okay, so I think problem C we have discussed. Any doubts, please ask. Otherwise, we'll move to the fourth problem. Any doubts, guys? Any doubts? Okay, we're moving to the fourth question then. Okay, so the fourth question is more ad hoc, right? And some math ideas. And I like the fourth question, to be honest, because it's not direct theory. You have to think a little bit. Uh, I could not solve the fourth question in contest. Actually, I solved it just 2 minutes after the contest ended. So I'm a bit sad about that. Like I had gotten the idea, but I didn't implement it properly in time. Anyways, um, you're given a starting point and ending point. Okay, Sx, Sy is your starting point. Tx, Ty is a ending point. We start at Sx, Sy. At any point, we can move to x plus m comma y or x comma y plus n, where m is the max of x and y. Now return the minimum number of moves to reach tx comma ty. Okay, so the problem is very straightforward, right? I'll just show an example and explain it. So let's say we have the first example 1, 2, 5, 4. Okay, S is equal to 1, 2, target is equal to 5, 4. Okay, so we have the following operations. We choose the max of the element and we can add it to any of them, right? So here x and y is equal to 1, 2. So max will be max of 1 and 2, which is 2, right? So that means from 1, 2, we can go either to 3, 2, or we can go to what? Either we can go to 3, 2, or we can go to 1, 4. Correct? That's what we can do. So now let's see how this goes, right? So we can go to 3, 2, or we can go to 1, 4, right? Now from 3, 2 again, we have two options. We can go to 5, 2, right? Or we can go to, no, wait, we can't go to 5, 2 because we have to add the max, right? So we have to add the max. So here we will add the max. So we can go to either 6, 2, or we can go to 3, 5, right? And we have completely gone in some other direction over here. So here we add the max. So we get 5, 4, or we get 1, 8. So this is the tree basically which is getting formed. Based on the operation, this kind of tree gets formed. Each time we can add the max to either x coordinate or y coordinate. Okay. So as you can see, this is our target, right? This is our target. And we can see that if we do this operation, then we do this operation, we can reach it in 2 steps. Reach it in 2 steps. So that's the answer, right? If we can reach it in 2 steps, the answer will be the minimum time it takes. So the minimum time is 2. Okay, does that make sense? Right? Now, one thing to observe is Sx goes up to 10 power 9. Tx also goes up to 10 power 9. So the coordinates can go up to 10 to the power 9. Okay, and that is the main crux of the problem, is that the coordinates can go up to 10 to the power 9. Okay, coordinates can go to 10 to the power 9. That's why we can't write a simple recursive solution. That's why we cannot write a simple recursive solution like brute force. We can't write brute force. Okay, what is the brute force? We simply start at the this node, right? We start at the starting point. We try both the options. Then from there we try both the options. And here we try both the options. We can see that this is exponential, right? So the number of steps it takes, it will become exponential, right? So we can't do that. Does that make sense? Okay. So how do we approach the problem, right? And so a lot of times, like in the DSU question we just had, thinking backwards helps a lot, right? So here we are thinking forwards, right? And if we think forwards, the answer takes exponential time. But what if we think backwards? And that will be our key intuition, right? Think about our operation backwards. Think about our operation backwards. So this is our key intuition, we can say, for the whole problem, is that think about our operation backwards. So our operation was what again? Let us recall our operation. Our operation was simply given an xy, we change it to x plus m, comma y, or x y plus m. Okay, where m is max of x and y. Okay, is that understandable, guys? So this is our operation. My first problem solution is not user friendly. Sure, I mean that is true, right? But in competitive programming, we're not exactly choosing to write user friendly code, right? We're trying to write code which is efficient and which we can write fast. So when I was solving problem 1, that's how I solved it in contest. Obviously, a much better way would be to use vector of pairs and then sort the vector of pairs, right? But I thought that that was not necessary for that problem, okay? So competitive programming is definitely not about writing clean code, although writing clean code does help that you don't get messy. But like problem A was just implement as fast as possible. So that's why I implemented it like that, okay? I don't think it's too ugly either. I think for the problem, it's not too ugly. Okay. So back to problem D, which we were discussing. So this is our operation. Now look at it backwards. Okay, look at it backwards. And what we're going to try to do is we have tx and ty, okay? And we will try to reduce it. Reduce it to sx, sy, okay? And now it's obvious that obviously sx and sy under this operation, they're only increasing, right? So that means that tx and ty, we should make it according to the operation, okay? So if tx and ty are not already less than sx, sy, we will repeatedly try to reduce them, okay? So we'll do this while tx is greater than sx or ty is greater than sy, okay? And we will do the reduce thing, reduce operation. We will reduce in reverse, okay? Reduce or reverse operation, okay? Now, when we're looking at it backwards, if you see a given a and b, that can become a plus m. Okay, so let us do one simplification, okay? Let us do one simplification. Let xy equals a and b, and we can write without loss of generality, or what that means is like it does not change the understanding for the problem, right? But we can write b greater than a. Assume b is greater than a, right? For now, just assume that. The opposite case also is the same. Okay, just the values get changed. Like just the order is different, right? So let's assume b is greater than a. Now let's think what are the values it can become. It can become a plus b, comma b, or it can become a comma 2b, right? If b is greater than a, then it can become a plus b comma b, or it can become a comma 2b, right? Is that understandable? Okay. So this is what it becomes, assuming that b is greater than a. Okay. So these are the two cases. These are the two cases we have in the problem. Right. So now if you want to see in reverse, if you want to see in reverse, let's say we have some xy and we want to see where this came from. Okay. Where this came from. Right. And now also we'll assume that y is the bigger one. Okay. Y is the bigger one. So either y is a plus b and x is b, right? Either y is a plus b and x is b. Otherwise, y is 2b and x is a. Okay. So if this was the case, then simply the previous operation would be x and y by 2, correct? And if this was the case, then the previous operation would be um, so the previous operation would be something like this. The value of b would remain x itself, and we'd have to somehow obtain the value of a, right? So the value of a will simply be y minus x, right? So we can say that this is where it came from. Okay. Does that make sense, guys? We're reversing the operation. Okay. So in reverse, there are these two operations possible: x comma y minus y by 2 or x comma y minus x. All right. So if we reverse the operation, forwards the operation was like xy becomes x plus my or x plus y plus m, right? In reverse, the operation becomes x y minus x, x y minus 2. Okay. Given that x is less than or equal to y. Fine. This is the condition. Okay. So this is how we see the operation in reverse. Operation in reverse. So I can show you an example. An example is something like, let's say we have 6 and 12. Okay. Then either it came from 6 and, or let's say we have 6 and 8. Fine. So then we can say that it came from either 6 and 4, right? Or it came from uh, 6 and 2, right? So these are the two possible cases it came from. Similarly, if we had 6 and 15, 6 and 16, let's say, either it came from 6 and 8 or it came from 6 and 10, right? So these are the two possible cases where it came from. Now the thing is, observe that this case is invalid, okay? This case is invalid and this case is invalid, okay? Why are these two invalid? Because think about it, right? Here the max is 6, right? But to make this, we're adding 4 to 4, which means we're adding the smaller value, right? But we can't do this. We can either go 610 or we can go 12 4, right? So 6 8 we cannot go. So this is an invalid place to go, right? Similarly, here this is invalid because the 6 is the smaller value, right? So we cannot add 6 to 10 and go to 6 16. Okay, we can only come using this direction, right? So the interesting thing happens is crux or core observation here. It's a core observation. When doing the operation in reverse, the operation in reverse, it looks like only one valid path is there. Okay, only one valid path is there. Okay, and I'll show you how exactly this is happening. And in fact, in one case there can be two valid paths, but in all the other case there'll be only one valid path. Okay, and why is that? Because in the first operation we're doing x comma y becomes x comma y minus x, right? But this operation is only possible if this y, if x was the larger element, right? If this x was equal to b, that's what we're assuming. So we're assuming that um, x is greater than y minus x, right? So this is the implicit assumption of the question, that x is greater than or equal to y minus x, right? So that means that 2x is greater than equal to y. Okay. So when doing in reverse, when doing in reverse, let x be smaller and y be larger. Okay, y be larger, right? What is the condition we have? We have that um, so x is, if we are assuming that x is the smaller element and y is the sum a plus b, right? So sorry, x is the larger element and y is the sum a plus b. So we must have that y minus x is less than or equal to x, right? Y minus x is less than equal to x, and we get y is less than equal to 2x, right? Right. So if y is greater than 2x and else y is less than equal to 2x, and we have a different option in these two cases. Okay. Now, if y is greater than 2x, then the only thing we can do is this, right? If y is greater than 2x, then we can do this. And this is, for example, this case. Here y is 16, x is 6, right? So 2x is 12, right? So if y is greater than 2x, we can only halve the larger element. Otherwise, if y is less than 2x, 8 is less than 12 here, right? 8 is less than 12. So in this case, we cannot subtract 6 from 8. We can only, sorry, in this case, we cannot halve 8. We can only subtract 6 from 8. Okay. So in this case, what we can do is y divided by 2. In this case, we can do y subtracted by x. Okay. So these are the two cases we can do. Fine. Mouse plus plus, mouse plus plus. And in fact, it reduces to these two cases itself, except if y equal to x. Okay, if at some position y is equal to x, then we can go both ways, right? We can go both ways. We can do both the operations. So if y is equal to x, then basically we come at some position where basically both the values are equal, right? So we have 3, 3, for example. So we can either go to 3, 0 here, or we can go to 0, 3, something like that, right? So if y equals to x, then we can go to 0x or 0y. It's the same thing, right? If y equals to x, then xy can become 0x and x comma 0, right? So this one applies only if y is less than equal to 2x. This one applies only if y is greater than 2x, okay? And if exactly y equals to x, then we can do this thing in two ways, right? We can do this thing in two ways. So that's why we have these three cases, okay? So now the way we will do this is, we will start with tx and ty, right? So that's our starting point, and we'll try to reach sx and sy, okay? So we'll say that while tx is greater than sx or ty is greater than sy, okay? Let ty greater than tx, okay? So how do we make sure that ty is greater than tx? Our logic assumes that y is greater than x, right? So we can simply swap ty and tx and swap sy and sx if needed. Okay, so if we swap both of them, the answer will not change, right? So if y is less than x, we can just swap both y and x. Okay, so let this be true. Now we can check if ty is greater than tx, then the answer is simply do y by 2, right? And increase the number of moves, right? Otherwise, oh yeah, and we can do y by 2 only and only if y is even, right? If y is even, right? Otherwise, we cannot do y by 2. Please be very clear on that because only even numbers can be resulting on doublings. So we have to try the exception, okay? So if y is odd, then we cannot do anything. We can't do the second operation. We can't do the first operation. So we can just break. Fine. We can just break. Otherwise, um, y gets divided by 2 and the number of moves increases by 1. Okay. Else, if ty is greater than or equal to, oh, and this should be 2 times tx. Sorry about that. This should be 2 times tx, right? That's what our condition was. That less than or equal to 2x or greater than 2x. So very sorry, this should be 2 times tx. 2 times tx. Okay, I hope that's understandable. Right. Now, otherwise, if ty is greater than tx, then we have only one operation possible, right? Which is y minus equal to x, and the number of moves increases. Okay. Now, what about that special case where ty equals to tx, right? In that special case, we can handle it separately. Okay. If we encounter this case, what we can say is if we have ty equals tx, so we have something like 3-3 situation or 5-5 situation, something like that, right? So no matter which direction we go, we can choose both the directions. We can choose to go 0-5, we can choose to go 5-0, right? And then we can keep reducing it something like this. So if we have, let's say, 6-6, then we can reduce this to 0-3 or 3-0, right? So basically, we can say that if we ever reach this position, the answer can be the same in both directions itself, but they can be swapped, right? 6-0 can become 0-6, 0-3 can become 3-0. So that's what the difference is. So we can have a flag variable, which means that they can swap. Okay. So we can have a flag variable, which will mean that swapping is allowed after this point. Okay. So I will do a dry run after this, or maybe an example after this, so you understand. But basically, if tx is equal to ty, swap will be true. Okay. Fine. Now that we have done this, at the very end of the problem, right? If tx equal to sx and ty equal to sy, simply return number of moves, right? Return number of moves. Now, if the swap is true, if swap, then we can test the opposite also. Tx equal to sy and ty equal to sx, right? Then in that case also we return moves. Otherwise, we return -1 because we cannot reach. Okay. Otherwise, we tried everything and we could not reach it. Basically, the idea is from tx and ty, if we do the operation in reverse, there's only one place to go to, right? Except in that special case where tx equals ty, always there is exactly one move to make. So we make that move and we go on. If we come to that move, that means that we can swap x and y, right? X and y are equal, so we can do either the operations on x side or y side. So in that case, we can note it and we have this. Okay. I hope the idea is understandable somewhat. Let's just look at the code and I'll explain with an example as well. Okay, so this is the code for the problem. We have sx, sy, tx, ty. This is the number of moves. This is the swap variable and set to false in the start. Okay. So yeah, So let's just write the final conditions, read the final conditions first. So Tx equals Sx, Ty equals Sy. In that case, we can just return number of moves, right? Otherwise, if the swap is on, then minimum of Sx and Sy should be equal to minimum of Tx and Ty. Maximum of Sx and Sy should be equal to maximum of Tx and Ty. If you see, this is the same condition over here, right? It's checking both the conditions at once. So that's what it's checking over here, basically. It's just saying that the minimum values are equal and the maximum values are equal, because then we can swap it and make it true, right? So that is return the number of moves in that case. Otherwise, return -1. Fine. Now we're doing this while Sy is less than Ty and while Sx is less than Tx. Okay. And this is the case if X is greater than Y, right? So if X is greater than Y, we are swapping to make sure that Tx is always less than Ty, right? Because that's how we discussed our cases. So I'm just ensuring that X is the smaller one and Y be the larger one, right? And we know that we can just swap Tx, Ty, Sx, Sy to make sure that Y is the smaller one. So this is to just ensure um, ensure that Tx is smaller than Ty. Swapping both Tx, Ty and Sx, Sy will not change the answer, right? Because they're just coordinates. It's like we flipped the coordinate system, right? Will not change the answer. Right, so that's why we can do this, right? This is just to simplify the cases. Otherwise, they would become 4 cases instead of 2 cases. Now, what is the next question? The next thing? The next thing is that it's just a break condition, right? If the swap is on and this condition is true, basically this condition, then we can just break. Why am I doing this? Because sometimes if the swap is not on, we can keep going in the wrong direction. So if this, sorry, if sometimes the swap is on, we can keep going in the wrong direction. So that's why if the swap is on, then if the swap flag is on, then we just check the condition and break immediately. Okay. Now here are the two cases. If Ty is greater than 2 times Tx, if it's an odd number, we can break. Otherwise, we divide by 2 and increase the number of moves. Otherwise, if Ty is just greater than equal to Tx, if Tx equal to Ty, we can swap. And then we subtract some value from Ty and increase the number of moves. Right? We subtract Tx from Ty and increase the number of moves. And when doing in reverse, we have only these two cases, right? Like I discussed, when we do this in reverse, we have two options. But the thing is, the nature of the problem is such that only one of the options in each case works. Unless x equal to y, in which case we actually have two options. But that case we are handling using the swap variable, okay? So then finally, when this loop finishes, either sx will be equal to sy or it won't be equal to. In that case, we can return the number of moves it took, okay? If the swap is on, then we can swap x and y, right? So in that case, we check minimum of x and y with max of x and y, and we return the number of moves. Can you tell why BFS from Sx and Sy gives TLE? I can tell you why that gives TLE. We discussed that in the very start, and that's because each time you have two nodes, right? So your depth increases by 2, fine? And so basically, if it takes 40 steps, right? Sometimes it may take 40 steps, right? If it takes 40 steps, then what happens is you will have to go to 2 to the power 40 nodes, right? You'll have to go to 2 to the power 40 nodes, which is too much for time limit, right? That's why BFS from Sx and Sy will give you TLE, because the number of nodes is too large. If you see, here, it can go from 0 to 10 to the power 9, right? So the time complexity of the BFS solution will be something like 2 to the power log of 10 to the power 9 number of nodes in your BFS. If you do from front to back instead of back to front, and that becomes 10 to the power 9 itself. That is too many nodes. So that is TLE. That's why we're doing from back to front. Because when you do front to back, there'll be two cases at each turn. Meanwhile, when you do back to front, there is one case at each time, except at one special occasion if x equal to y, which we are handling. Right? So that's why my solution will be, the time complexity will be log of, the solution will be big O log of tx plus log of ty. This is the time complexity of our solution. Okay. And we can just rewrite this as time complexity of big O of log of x, right? Where x goes to 10 to the power 9. So this is the time complexity of our solution, which I told. If you use BFS, then the time complexity will simply be big O of x, and x goes to 10 to the power 9, so it won't be possible. Okay. X is the max value of any coordinate. Okay. Yeah. When we go backwards, there are only two cases possible. That's why we are, when we go backwards, there's only one case most of the time. That's why our solution does not time limit exceed. Okay. So I think that does covers all the problems for the contest. If there are any doubts, put it in the chat. If you have any general questions regarding CP, that also you can put in the chat and I'll answer it now. Right? Any doubts, please put it in the chat. Now is the time to ask doubts. I know it's early in the morning and yesterday also there was CF, tonight is also CF. So not many people will do Leetcode today, right? So there are less viewers, I guess. But even you, if you have any doubts, just ask because um, I'll be able to spend more time answering it, I suppose, since there are less people today. CFD yesterday, I've not solved it yet. I guess we'll have to wait for the editorial for that. If you're in TLE, then maybe if you make a doubt, right? Some mentor will solve it and tell you how to do it. I have not solved it yet. I plan on upsolving it today. Is the editorial out? The editorial is not even out yet. So I guess you can read comments or read other people's code if you want it urgently. Otherwise, wait for the editorial, I suppose. Okay, guys, it looks like there's no more doubts, so we'll be ending the session now. Thank you for attending, everyone. Hope you learned something. Definitely do check out TLE Eliminators self-paced courses if you haven't already. And see you in the next PCD. Bye.